Thank you very much. Hello, everyone. Our project is real-time region-constrained visual counterfactual explanations. Together with Janek, we will present our work. The project advisors are Bartłomiej Sobieski and Przemysław Biecek, who we are really thankful for their guidance and support throughout the year. So our work is a direct extension of a recent paper by Bartłomiej Sobieski et al. Called Rethinking Visual Counterfactual Explanations Through Region Constraint. What are VCs and what are RVCs? VCs are modified versions of images that show how minimal changes to the input can alter a model's prediction, helping users understand what influenced the decision. So we have an example of that at the right of the slide. At the top of it, you can see an example of a visual counterfactual explanation, VCE, where we don't care about regions. We can mask an entire picture and generate an explanation based on the entire picture. Whereas in RVCs, we care about the locality of explanation. So you can see that at the bottom, we have Jay and Bulbul in both examples. And here we only look at some mask, some subset of the picture, some subset of the pixels of the picture. So the problem is the single explanation generation is pretty slow. It takes around 13 minutes on Mac M1 CPU and around 50 seconds on an RTX 3090. Our project had two main goals. One was to design and implement a nice GUI that would basically like a UI that would enable users to interact with the explanations without having to code and to speed up the underlying model to achieve real-time possibilities. So let's start with a quick look at the GUI. The GUI includes an image drawing canvas, so the users can upload images, can draw some masks for the explanations. We have a random image sampling generator, so we can draw some images from the ImageNet. If you don't want to draw a mask, you can generate it by prompting Langsam model. It will generate it for you. Also, you can generate masks based on the underlying attribution model, which right now is integrated gradients. So you just get an automatic mask that is quite semantically meaningful. We also have a server address configuration where users can host the backend server for the GUI themselves and different configurations for the explanation algorithms. So now let's talk about the real-time interactivity. The first approach, let's say the low-hanging fruit approach, was to do something simple. So here you can see different method components that we are interacting with. Janek will cover it in some detail, like each component. Right now, we only care about the fact that with the first approach, we didn't try to modify any of the underlying components, but rather try modifying input to one of them, the diffusion probabilistic model solver, which is a stochastic differential equation solver. And we wanted to check if modifying the input to it would result in some speed up. So the underlying process is continuous, and we are approximating the solution to it with some discrete steps. In the baseline, the steps are uniform. So here you can see the different plots at the bottom, and you have different respacings of the timestamps. The baseline one is the uniform one, the one at the left, and the one that gave us, so basically like you do, throughout the timeline, you do the same amount of steps with the same length. And we tried different respacing strategies. And the one that worked best for us was the dense sparse one, which is the one in the middle. So you, at the start of the process, you do less steps, and then you do more steps later on. Here we have two metrics that we use to evaluate how good different respacing strategies are compared to the baseline. So on the x-axis, you have number of steps going from 50 and up to 100, which was the baseline number of steps. So the bold one is the dense sparse one. And you can see that we achieved quite a good flip rate. Flip rate tells us how like basically the accuracy of flipping the class. So J to Bulbul or just horse to zebra, whether it happened. Of course, we want like as close to perfect accuracy as possible. The other one is LPIPS metric, which is a learned similarity metric between two different images. So it tells us basically like if we flip a horse image to zebra image, we also are interested in something that is semantically meaningful. So we want the zebra to be as close to the original horse picture. And now Janek will talk about a different research approach that we took. Janek, the floor is yours.
Okay, thank you, Michał. So to further describe our approach, we need to take a deeper look into method components that goes into this region constraint counterfactual explanation. And the main two components of the methods are the inpainting method, which in the case of the base work are image-to-image Schrödinger bridges, and the underlying diffusion probabilistic model solver, which in case of the base work is DDPM. There is also the guidance component of the method, which has many improvements. It's because we don't want to generate any images, but we want to generate counterfactual explanations. So this is conditional generation problem, which is very unstable by default, and you need many tricks to stabilize this process. So the base work introduced many tricks in this guidance component, and then we have region selection methods. So for example, integrated gradients. So we tried modifying one of these components, which is we wanted to swap the diffusion probabilistic model solver for a better performing one. In the process, we discovered a possibility for improvement, for improving this one of the components in the guidance, one of the guidance tricks. Okay, so what is this DPM solver? This is an improvement to baseline stochastic differential equation solvers. The distinct feature of DPM++ is that it's not only a first order approximation solver, it's second order approximation solver. Therefore, it is more stable than the first order approximation methods. And this is a picture from the original work provided by the authors. We can see that even with low number of steps, so a number of function evaluations, originally we can generate images using 100 steps, and we can decrease this number even to 10 steps and retain the semantics and quality of the image using the DPM solver++. But using the default DDPM solver yields very different results, generating similar image with different number of solver steps. So that's why we wanted to implement DPM++, because by using it, we can severely decrease the number of function evaluation calls. Okay, so what are the assumptions of this algorithm? So the first thing that this algorithm assumes is that the underlying diffusion model that generates images has a simple linear form, which is rather classic. So there are two components of the diffusion process. So the goal of diffusion process is to, starting from an image, destroy it continually into Gaussian noise. And we can parameterize this process in various ways, but one simple approach is to have a linear parameterization where at time step t, we have a drift parameter alpha, which tells us how much of the original image is left in the image at a given time step, and noise scale sigma, which tells us how much noise is added to the image. So the DPM solver works in this very special and easy case. But more general score-based generative modeling is not of this form. And the used image-to-image Schrödinger bridges in the work are those more general score-based generative models. So how those core-based generative models work? They also destroy original image into noise, but they don't assume the special form of the forward process. They assume more general formulation, which may be nonlinear, and it can be derived. The backward process can be derived from the formulation of the forward process. In the case of image-to-image Schrödinger bridges, we have an original image and we have a target image. We want our original image. We want to destroy our original image in some particular way. So, for example, in the case of in painting, what we want is we just want to mask regions of the image. So the final image should not be pure Gaussian noise, but should be only noise at the masked region of the image, and outside the mask, the image should be intact. So this is a much different process, and it's nonlinear in nature. The image-to-image Schrödinger bridges are like barely tractable. Like they're general Schrödinger bridges, you cannot sample from them, but image-to-image Schrödinger bridges are special case of Schrödinger bridges from which the sampling is tractable. Okay, so we want to adapt the DPM++ to image-to-image Schrödinger bridges. The first obstacle is that the image-to-image Schrödinger bridges have many more parameters than the original diffusion problem. For example, we have 2 drift parameters and 3 noise scale parameters. So it's not entirely obvious which parameters should we choose to parameterize our solver. So we have original image and masked image. And we want what we want is we have parameterization. We have this linear parameterization. So we can write down the posterior conditioned on the source and the target image from the DPM from the image-to-image Schrödinger bridge paper. We can choose only optimal transport path. And in the case of in-painting, the target image has special form that lets us write it down as the direct sum of original image and noise component. And by rearranging the terms, we can arrive at the formulation that is susceptible to the original formulation. And if we plug in those parameters into the DPM solver, we can indeed see that we can recover the original image. Okay, so by this, we also discovered a different way to parameterize this guidance scale that we will not go much deeper in this presentation. We can parameterize this guidance based, we can give it a time-dependent schedule and not a fixed schedule as in the base work. Okay, so what are the experiments? We took ImageNet dataset. We took a horse class, which is 650 images. And we wanted to generate counterfactual explanations. Basically, we want to flip an image of a horse to similar image that the classifier predicts as a zebra. And we choose a region constraint automatically to be 30% of image area chosen by integrated gradient. And we evaluated our algorithms with different number of evaluation, number of functional evaluations, 10, 30, and 50. We will be mostly interested in the case where number of function evaluation is 10, because then the image generation is the shortest. We will track flip rate. So if we manage to change the decision of a classifier or not. So we can see that the results group there are 2 groups of lines. There is red and green line, which are using our schedule, which is more graceful towards generation. And there is blue and yellow line, which introduce more changes to the image. So the flip rate for those blue and yellow lines is higher. However, the flip rate is in tension with evaluated semantic similarity and distance from of the original image to the generated counterfactual, because if we change the image more than not, then it's easier to change a prediction of a classifier. So those two metrics are our intention, and I think with our approach we strike a good balance between the flip rate and the similarity. So to finish our presentation, we present some examples. Using 10 number of function evaluation calls, which you can generate in just 5 seconds on 3090. So the first case is the simplest one. On the top row, you can see our introduced noise schedule. Compared to the bottom row, the colors are more toned. There is no solarization effect of the colors. And using the DPM++, you have more defined zebra features on the horse. In this case, you see it's somewhat adversarial, because the integrated gradients masked a region of an image that is not a horse, but is a woman. And you can see that basically all the methods severely deform the woman. However, by using our schedule and DPM++ solver, you get zebra features on a horse, and the woman is not that much modified. And final example is where we have two horses on one image, in which case all of the methods failed because they merged two horses into one. And we think that all of those methods didn't provide a good result. Thank you for your attention.
Do we have any questions? If not, so I'm curious about this bridge part, right? Because if I understand, you are starting from an image, you are finding a subset of an image that you want to modify, right? So is this part like in the middle of the bridge, or is it because in the bridge, so usually distributing in bridges we have like two concrete let's say samples at the beginning of the end. So was this, let's say, end or the beginning?
Yes, so the beginning is original image, and the second end of the bridge is the source image destroyed in particular way. And in our case, in the case of in-painting, it's a masked image. Yes, so we have original image and a masked image. And Schrödinger bridge is a gradual process deforming, basically noising out the masked component of the image.
And you are only constrained to this masked part?
Yes, yes. You leave the original image intact out of the mask region.
Yeah, and the mask can be whatever you want, right? Like that's why we created the UI, so the user can like say that could be like a doctor and saying like looking at some cancer images and saying, okay, like we only care about this region and what happens, right? But you can also use some automatic methods such as integrated gradients or something else.
Yeah. Cool. Thank you.
Thank you.
Thank you.
Any other questions? If not, so